Hello together. Today I want to discuss with you the problem how to check the stability of an RF amplifier. And here I sketched a measurement setup. So as central element we have here our RF amplifier or an active device. And the input of the RF amplifier is absorbed. So if we use a 50 ohm system, so we would have here a 50 ohm resistant, and the amplifier will work into a spectrum analyzer, and this spectrum analyzer has normally a 50 ohm input impedance. So we talk about a 50 ohm system, and if we first do not connect our DC power supply to our amplifier, we will just see the so-called noise floor in our spectrum analyzer. And if I now connect our DC source to our amplifier here, so I connect the DC source here, and what will happen then? As long as our amplifier is stable, the amplifier will just amplify the noise of our 50 ohm resistant here, and of course maybe the noise floor will come up again a little bit because it's now the measured noise floor will now increase a little bit. So under these circumstances the amplifier would be stable. So, but what will happen if it's unstable? If it's unstable, even though we do not give any signal into our amplifier, despite the noise, if our amplifier is unstable, then we will see here some spikes, which means that our amplifier itself will produce a signal by itself. And now I want to discuss this circuit. If I describe this circuit with the help of the Y parameters, so normally we can also describe the whole amplifier or an active device with the help of the Y parameter. And now, in contrast to this situation, I use an arbitrary generator admittance at the input, and I use an arbitrary load admittance at the output. And how can I describe now the instability or the point of instability? The point of instability will be reached if the voltage U1 and U2 will exist without an input signal. U1 will be unequal to 0, and also U2 will be unequal to 0. This is the here it must be 0. So if I have an unstable amplifier or unstable active device, this voltages U1 and U2 will exist even though I don't give an input signal to our circuit. So now I want to go on in our consideration, and now I want to discuss with you the question how to understand the existence of U1 and U2. So we saw in the preceding section, we saw that the voltage U1 and the voltage U2 will exist even in the case if our amplifier or active device is stable. What I did here is now to set up the equivalent circuit of this active device, which is described by our Y parameter. So this is the internal circuit of the Y parameter, or this is the circuit. With the help of this circuit we can describe the equations of the Y parameters, and we have here an arbitrary generator admittance, and we have here an arbitrary load admittance. And now the question arises, how can these voltages U1 and U2 exist even though we don't feed a voltage into our amplifier. To discuss this point, I split up our amplifier or our active device into two parts. I call this part the so-called forward part, which consists of the voltage U1 at the input. This is this voltage here, but I assume that I use in principle a voltage source to generate this voltage. And in the forward branch we have then the parameter Y21 times U1, which will generate a current in this loop here, and of course the total current will flow against this loop here. And so the current will flow in this direction. So if I set up the equation, then I can say the voltage U2 is given by the current, which is Y21 times U1, divided by the admittances, and we have a parallel admittance here, Y22 and YL. On the other hand, there will exist now a feedback, and this feedback is described by our parameter Y12. In the ideal case, the feedback would be 0, but this is not the real case. So in a real amplifier or in a real active device, there will always exist this parameter Y21, and this will be responsible for a current in this loop. And again, the current is flowing against the direction of our voltage U1 prime, and we will get for the voltage U1 prime, it will be given by minus here because of the directions, and Y12 divided by Y11 plus Yg times U2, and we can define now two parameters. One is the voltage gain of our forward branch, and one is the feedback parameter Ku, which describes the feedback of the output to the input. So the idea behind the point to look how this voltage is U1 and U can arise without any voltage at the input was that I split our transistor. Of course, this is only possible on a theoretical base. I split the transistor in two branches, in a forward branch and a branch which describes our feedback. So if I sketch this voltage U1 here, I assume that I insert or connect a voltage source of U1 to this input of our transistor, and then we saw, due to the feedback, there will also be generated a voltage U1 prime. And of course we can now calculate the voltage U1 prime, and the voltage U1 prime will just be Ku times U2, and the voltage U2 is just Vu, the voltage gain of our forward branch, times U1. And you see, as soon as the voltage U1 prime would be equal to U1, I can in principle connect the both points, and then this voltage will be equal, and I don't need to connect a voltage at the input here, and this would be then the condition for instability. As soon as I connect these 2 points here, I force U1 prime to be equal to U, and this is only possible if Ku times Vu will be equal to 1. And the same, of course, I can insert now this equation, and then we will find this equation for our active device or our amplifier to become unstable. So our active device or our amplifier becomes unstable as soon as this equation holds true. So up to now we discussed the condition for instability. What does it mean? I consider the active device or an amplifier, which is terminated in a certain generator admittance and then a certain load admittance. And we saw that if this system is unstable, the voltages U1 and U2 must exist, even so we do not feed any voltage into the system. And we found that under these circumstances, this equation holds true. And now we can rearrange this equation on mathematical base. For example, this term can be brought to here, and though we end up in this equation, and we can also now bring this equation on to this side, and then the final equation would read like this. And in the same sense, we can do the same with this part of the equation, and then we end up in a very similar equation. So if this equation holds true, also this equation and this equation hold true. And now is the question, what does this term mean here? So especially this term, if you have a look to this term, then this is nothing else but the input admittance you will see into our amplifier or active device. Because of the feedback, also the load admittance will have an influence on its input admittance. And on the other hand, on this side we will have the same. So this part will be the output admittance I see into this. So I call this Y out. So we can write now that the generator admittance plus the input admittance must be 0. Or we can write that the load admittance plus the output admittance must be 0. So we can see that this condition here for the transistor to be unstable is equivalent to this condition here, that the whole admittance at the outputs vanish, and also to this condition that the whole admittance at the input vanish. And this will give us the chance now in the next video or in the next lecture to discuss under which circumstances our active device or amplifier is stable. The starting point for this consideration will be this equation and this equation.